Hello everyone. So today we'll be solving this message route problem from CSES. Now this problem speaks about like the Serjala's network. I don't know whether I'm saying that name correctly, but yeah, just bear with me. So it says like this network has n computers and m connections. Okay, and our task is to figure out whether ULOV can send a message to Maija. Okay, and if it is possible, what is the minimum number of computer on such a route? Okay. Now, Yulovi's computer is 1 and Maija's computer is n, and every connection is between two different computers, and so there are no self connections. Okay, so by self connection I mean something like this to this. Okay, we do not have this case, which is good for us. Okay, so every connection is between two different computers and there is at most one connection between any two computers. Okay, cool. So uh, let's take this example. So if I draw this out, so this will look something like this. So we have a edge 1 and 2. Okay, and then we have another edge from 1 and 3, then another edge 1 and 4, then we have a connection between 2 and 3, and then we have a connection from 5 to 4. It's not 5 to 4 because these are all undirected graph. So like 4 to 5, like 4 and 5, we have a connection. Okay. Now from this graph visualization, you can simply see like we have a path from 1 to 5, which is this 1 to 4 and then 4 to 5. We have this path. Okay. Then we also have other paths like from 1 to 2, then from 2 to 3, then 3 to 1, then again same 1 to 4 and 4 to 5. Other path will be like from 1 to 2 we can go to 2 to back to 1, then 1 to 4, then 1 to 5. Okay, like this we have many paths, and the question demands us to figure out what is the minimum number of computers on such a route. Okay, it also tells us like if there are no routes where we have to print impossible. So in this problem we have two problem statements, like sub problems you can say. But is first is like whether we can reach from 1 to n. Okay, whether any path is there. Okay, that's a question mark for us. Okay, then second is if path is there. Okay, I'm just writing a ternary operation here. So if path is there, what is the minimum path length? Okay, if path is there, what is the minimum path length? Or not just not to confuse, I can say if path is there, what is the minimum path length? Okay, now minimum path length basically speaks about how many number of computers are there in the path. Okay, number of computers. Cool. So here you can see the shortest path will be, we can go from 1 to 4, then 4 to 5. Okay, this is our shortest path. Okay, now to solve part 1, like whether there is any path from 1 to n. Okay, we can use either DFS or a BFS. Okay, we can either use both of them, but the thing is uh, here BFS will be much optimal than DFS. Reason being, let's look at this graph. Okay, so if I do a DFS, let's first draw the graph. Okay, 4, 5, and we have this connection. Okay, now in DFS, if we consider the worst case. Okay, by worst case I mean, so from DFS how will we, so from 1 we will be traversing to uh, like to its neighboring node, from the neighbor node we will be again doing a depth first traversal, right? So let's say something like this happens. So we start from 1, then we go to 2, then from 2 we go to 3. Okay, now from 3 it doesn't have any connection. Like it has a connection from 1, but 1 will be already marked as visited, right? So from here we have to backtrack. So back to 2. Then from 2, both of its neighboring node are already like visited. So then again we have to backtrack. So from 2 to 1. Okay. Now from 1, this 2 and 3 will be visited. Then I will be going to 4. Then 1 to 4. Then from 4, again the DFS I will be calling to 5. Okay. Like this. Now you can see the minimum, like the number of steps I'm taking in order to reach 5. Okay. So like this will give me the minimum path. Okay. There is no doubt in that, but you can check the minimum number, like the number of steps I'm taking to calculate the minimum path, because I have to complete the whole traversal, right? So it's like 1, like 1 to 2, then 2 to 3, then once we are at 3, we do not have any other neighbor nodes, so 3 will again go back to 2, then 2 to 1, then from 1 to 4, then finally 4 to 5. Okay. So we have like 1, 2, 3, 4, 5, 6. So we are taking 6 steps. Okay. Now let's see how it works in BFS. 3, then we have 4 here, then we have 5 here. Okay. Now in BFS, what do we do? So so we have a queue. Then in the queue we put the source node. Okay. Then from source node we spread. Okay. So by spread I mean, so in DFS you can see, so from the source node I go to its neighboring node and then again do a DFS, right? So you can see there's a linearity here. Okay. But if you check BFS, BFS is something like I have a source, then whatever node it is connected to, I directly like put them in the next iteration. So I go from here, here, and here. Okay. But DFS doesn't do that. Even if this node is connected to some other node, it first go to the entire depth of its current node and then it traverse back. Okay. Or you can say backtrack. But here we do not backtrack. From this source node itself, we just go. And we go like we spread unless we are not hitting any leaf nodes. Okay. So you can see a spreading behavior here and there is a linearity behavior here. But time complexity wise, if you see, like both of them have the same time complexity, which is like number of nodes plus the number of edges that we have. Okay. But if we compare them on the basis of their runtime, okay, runtime of DFS will be bigger than runtime of BFS. Okay. Now, another beauty of BFS is that we can use a BFS on a undirected and unweighted graph, and we can directly get the minimum distance from source node to all the nodes. So that's another beauty of BFS, because when we are doing a BFS, we are directly jumping into the neighboring nodes. We are not doing any backtracking, because if I would have to do the same thing in DFS, I always have to backtrack, like from 1 to 2 to 3, then I'll be updating their distances here, and then again I have to backtrack. Okay. Like first I have to reach 3. Now initially when I'm doing from 1 to 2, then 2 to 3, here distance for 2 will be 1 and for 3 it will be 2. Okay. But when I'm doing the backtracking and then again starting from 1, okay, I already have an edge from 1 to 3. So the actual distance should be 1. but this updation will only happen when I'm done with my backtracking. So you can see, like, if I do the same thing on the BFS, so from 1 to 2, like from 1 I will be spreading to all its neighboring, like neighboring nodes. So I will be already assigning them their final distances, which is 1 1 1 here. There is no backtracking happening here. I'm directly assigning them their minimum distances from the source node. Then from 4 I'll be spreading, okay, and I will be assigning 2 here, okay. So yeah, if you compare them on the basis of their runtime, so BFS will be much faster than DFS, okay, and we can directly get the minimum distances from from our source node to all the nodes, okay. Now if you guys are familiar with Dijkstra, I hope, Dijkstra algorithm, which is kind of the very standard and powerful algorithm to compute the minimum distances from source to all nodes, okay. Generally its use case happens in like when all the edges have a weight in them, okay. We generally use Dijkstra there, okay. So if you see the implementation of Dijkstra, it is very similar to what we have in BFS, okay. But the same thing we cannot apply here. Like when we have weighted edges, we cannot apply a BFS. Reason being, BFS assumes that when it is spreading to the neighboring node, the weights are unweighted, okay. If there are some weights assigned here, let's say this is 10, this is 12, this is 15, okay, it doesn't take that into account because BFS only computes the minimum distance based on the number of edges that it has between the source and the node, okay. So yeah, cool. So I hope you understand the difference between BFS and DFS. Now let's talk about, so for 1 and 2 we can apply BFS and we can get the answer, okay. Now let's talk about the implementation of it. Let's clear up this, okay. Now for the implementation, when I am computing distances in BFS, okay, I will be having a data structure which will tell me what's the distance from source to the node, okay. uh, Distance from my source to any node, let's say node I, okay. And I will also be using another data structure which is parent, okay. Now this I'll be using to answer the this thing. So they have said that you have to compute the minimum number of computers on the valid route, and after this we also have to print the route, okay, and we can print any valid solution. So I will be using parent for that. Now how parent will work is, so whatever final path I will be getting, okay, so parent will be storing the immediate uh, parent node for every node, okay. So by immediate parent I mean, so let's say I have 1 2 3 and 4, okay, and let's say this is my final answer, okay. Let's say something like that, something like this is there, okay. Now how my parent will look like is like, for 1 it will be storing 1, for 2 it will be storing 1, okay, for 3 it will be storing 2, okay, like immediate parents. For 4 it will be storing 3, and finally for 5 it will be storing 4, because in the path you can see, like when I'm at 5, I reached 5 when like only after I was at 4, okay. Now this will help me to backtrack the path from my destination to source, okay. So distance and parent, this two new data structure I will be using. Now how distance, how I will be using distance is like, so I will initialize my distance with all the nodes, okay, and the value here will be a maximum number. Okay, so if I'm using int, then I will be using int max. Then if you guys are using, let's say, long data variable, like the long data type, then you will be using long max. Okay, so any max number of your choice. Okay, now how I can use distance as my visited is like, so from BFS, what do we observe? So when I am at a node, I'm basically spreading to all its neighbor, right? Okay, and if I say, once I have compute once I have compute or once I have computed the minimum distance from my source node to any node, okay, then I will not look at that node again. Okay, so when I am starting from my source and then I'm spreading to all this node, okay, now this will now when I'm at this node, I will not be getting this node in any other iterations. Okay, so whatever minimum distance I will be computing for this node, okay, from for all these nodes, okay, so that will stay constant. Okay, once I have decided what is the minimum distance from this to this, there is no chance I will be updating that again, because I am doing a spreading. So in the first iteration, whenever I am getting this node, I have already finalized the weight. Okay, so my visited condition will be, if my distance of a node, okay, is not int max. Let's say int max is the maximum number I have taken. Okay, then this means I have already visited this. Okay, because initially what I am doing is uh, I'm initializing the distance vector with the int max. Everyone is int max. Now when I have a value for a node which is not int max, then that means I have already finalized the distance of that node to my source node. Okay, so using this two data structure, I will be able to solve this problem. Okay, so I guess I have talked a lot about like how to do this. It's better to show like how we will be achieving this all things like in coding. So let's directly jump to the coding part. Okay, so yeah, so let's first take the input. I have n here, m here. Okay, then uh so n is the number of nodes and m is the number of edges. Now I will initialize my graph. So I'll be using a adjacency list. So n plus 1, because all the nodes are 1 base indexing. So y2 again do minus minus for to convert them into a 0 base indexing. So let's take n plus 1 directly. Okay. Then the number of edges. Let's say a b b, then graph of a, push back b, then similarly for graph of b or a. Okay, so graph is done. Now let's create our distance and parent vector. Okay, int max parent n plus 1. Okay. Now a simple initialization is like so for each of the node initially all of them are parents of itself. Okay. So this will look something like this. Okay. So this is how my parent will look initially. Now I will be coding the BFS solution. Q dot push. So I will be starting from 1. Now while my queue is not empty. Okay. So I'll be writing BFS code here. Then this is, then we have a node here. Okay. Then queue dot front. Then I will be popping that element from the queue. Then I will be traversing to its neighboring nodes. Neighbor node of graph node. Okay. Now the visited condition here will be if my distance of n node is not finalized, if it is still int max, then what I will be doing is distance of n node will be distance of this current node plus 1, because whenever uh, I'm at n node, I can only reach to n node unless I have visited n node, right? Like this node. Okay. Now if I have visited this node, that means I have already finalized the distance for this node. Now from this node to this node, the number of edges in between is 1. So the distance will be distance of this node plus 1. Okay. Then parent of n node will be a node, and I will be pushing this n node to my queue for the next iteration. Okay. Okay. Now also one more initialization I have to do is, so distance of 1 will be 0, because from 1 to 1 the distance is 0, right? Cool. Now how will we check whether we have a path from 1 to n? So if I have a distance of n not equal to int max, okay, then this will tell me like, hey, I have figured out a path. Okay. I have figured out a path from 1 to n. Okay. And it has a distance not equal to int max, right? So if I simply check if dist of n is equal to int max, then I haven't figured out a path from 1 to n. So there is no path. Then I can simply type in impossible. Okay. Now, if this is not the case, that means we have a path. Okay. Now, distance basically tells me like if I have this, or let's take this one only, 1, 2, 3. Okay. Now, distance will tell me for 1 to 1, I have 0. From 1 to 2, I'll have 1. Then from 1 to 3, okay, I will have 2. Then for n, like 1, 2, 3, I'll be having 3. Okay. But we do not have to say how many connections we have. We have to tell how what is the number of computers we have in such a route. Okay. So it's basically the number of connections or edges. Okay. Or the distance of n plus 1. Okay. So this is for or plus 1. Plus 1 being because I'm counting the source also. So distance of n plus 1 will be the number of computers I'll be having in that path. Now we have to print it. Okay, so let's create our a vector to capture all the nodes in our path. Okay, now I'll be using my parent vector now. Okay, so I'll be starting from n. Okay, then I will backtrack to 1. So while now the termination condition will be while node is not equal to 1. Okay, while node is not equal to 1, we are starting from n. I'll be pushing this node. Okay, so how it will act is like, so here now, so I'll start from n, then I will go to this 3, then I will go to 2, then I will go to 1. Okay, now for 1, parent of 1 will be 1. Okay, so I'll be stopping my iteration. Okay, so this is done. Okay, now so my answer will be storing a path something like this: n 3 2 1. Okay, we have to print the reverse order, so I have to reverse it. Okay, and then I will be printing all the nodes in path. And then finally a new line character. Cool. Now let's quickly run this on this test case. Okay, we got an error. It says dist was not declared. Oh, I took distance. I can make it dist. Okay, we got another error. Let's see. It says, oh, okay, I have used dist. Okay, I guess we should change it to distance. Distance. Okay. Anywhere else? Cool. So we got 3, 4, and 5. Okay, so 1 is missing here. Reason being, I'm stopping my iteration when I'm at 1 itself. Okay, so what I can do is I can insert a 1 in my path after this backtracking. Cool. So because when I was backtracking, so I was traversing from n to 3. Okay, then I was traversing from 3 to parent of 3, which was 2, then from 2 to parent of 2, which was 1. Okay, now my stopping condition was when parent is of a node was not equal to 1, but I was not, so when I had this condition I was not picking up this node, so that's why 1 was not printing. So I can manually insert a 1 into my path. Cool. So let's again run this. Cool. Now let's quickly submit this. Cool. All got accepted. Now let's quickly do the time complexity analysis and time, and then we will jump to space complexity. So time complexity wise, so I'm building my adjacency list, but it's not taking any other operations. Okay, so whatever input I'm getting, so whatever edges I'm getting, I'm directly inserting them to my adjacency list. So we can ignore the time complexity because this is same as the input. Then after this initialization, this is linear. This is also linear, and this is also linear. Okay. Then, or let's write it down. So initialization of distance, initialization of parent, then again updation of parent, all are like the number of nodes that I have. Okay. Then the BFS. Okay. So here you can see like this is like the standard code of BFS. We are not doing any fancy operation. All of the operations are constant here. Okay. So it's the standard BFS time complexity, which is number of nodes plus the number of edges. Okay. Then after this, I have this. This is a constant time condition. Then this. Then I'm updating the path. Okay. Now here, this is a backtracking logic. Okay. Now, what will be the worst case here? So if I have a graph, something like this. Okay. So here path length, let's say 4 is my destination, 1 is my source. Okay. Now here, the path length will be 1 here. Okay. Which is less than my number of nodes. Okay. So the worst case the worst case will be like when I have some kind of a linear graph, 3 and 4, because now in order to reach 4 I have to traverse it linearly. Okay, so this will be the worst case. Now in this worst case, you can see the number of traversals I'll be doing, or the number of times this for loop will be running, is the number of nodes that I have. Okay, so this will, the worst time complexity of this will be order of n, or the order of number of nodes that I have. Okay, then I have a reverse, which is again a linear. Okay, then I am printing the answer, which is the number of nodes in the path. Okay, so this will boil down to, so all of them are linear. This is like more than all of this. Okay, so the worst time complexity will be the standard BFS and DFS time complexity, which is n plus c, the number of nodes plus number of edges. Okay, now let's quickly do the space time complexity. Okay, so we will not be considering the graph for space complexity. Let's look at extra spaces that we are using. So we are using a distance, but this is increasing linearly. So this is linear. Okay, then we have parent. This is also increasing linearly. So we go of n. Then I have this queue. Now queue will be storing the number of nodes at one instance. So number of nodes again. Okay, then I have this path. So we have already seen. So the worst case will happen when I have a linear graph. Okay, so path will be big of n. Okay, then we have this. So yeah, after this, no more operation. So yeah, all of them are linear. So space complexity is the number of nodes that I have. Cool. So these are the time and space complexity of this algorithm. Now, yeah. So if you still don't understand like a couple of parts in this explanation, you can directly comment in the YouTube section. I will try to answer your query. But I hope you guys learn something new. Okay. And yeah, I hope you learn the about the implementation and how we are using BFS here. Okay, and the difference between DFS and BFS. So yeah, so just stay tuned to watch more videos on this. So I'll be uploading more videos on CSES graph solutions. So yeah, thank you all for watching.